This is Module 17, Lesson 1. It is our last module. We have 2 lessons this time. They are pretty simple in what you're being asked to do. It's a combination of concepts and something to do. So let's get started. As you can see, we're talking about radioactivity. You have the definition of radioactivity on the screen. You need to know that. It's simply whenever a nucleus breaks down and falls apart and it gives off stuff. It can either give off energy, it can give off matter, or it can give off both. You also have the definition of radioisotope. The radio part of this means that it's radioactive. The isotope part we did a long time ago, back in module maybe 3, where we talked about how you have isotopes of elements. So just as a little bit of a review, remember that an isotope is an atom of an element that has a different number of neutrons from normal. And remember we wrote isotopic symbols. I know that this has been a long time ago, so hence the review. So for example, if you could remember writing them like this, when we wrote them this way, the top number referred to the mass. This was the mass number. And this bottom number here is the atomic number. So remember that the bottom number determines the identity of the element, and then of course you have the symbol. The mass number can change. So for example, if we have 12,6 carbon, this is carbon 14 on the left. It has a mass number of 14. This is carbon 12 on the right. It has a mass number of 12. They're both still carbon because they have the exact same atomic number on the bottom. That makes them isotopes of each other. They're the same element. What they have is a different number of protons and neutrons. So remember when we did this, if we look at these, I'll quit switching colors here in just a second. This one has 6 protons and it has 6 electrons. This one has 6 protons and 6 electrons. What's different about them is the number of neutrons. This one has 8 neutrons because we subtracted the number of protons from the mass number, and this one has 6. So as you can see, they have the exact same number of protons, they have the exact same number of electrons. What's different here is the number of neutrons. That makes them isotopes. So when we're looking at these, the reason for going through this much of this is because we're going to be looking at these symbols a lot for some nuclear decay equations, and I want to make sure that you remember how to interpret these little symbols. So let's look at 3 main types of radiation. We have alpha, beta, and gamma. Now, you don't really need to write anything down from this slide because I have screens after this that give you the information that you need in your notes. And then we have neutron decay. I'm just using this to kind of point out the idea that they're not created equal. Alpha, as you could see, is stopped by the person's hand. Beta, though, would go through it and would be stopped by a piece of aluminum. Gamma rays or X-rays, those are only stopped by lead. So remember when you have X-rays like at the dentist office and they put the apron over you, or if you've ever had X-rays of a broken bone or a possible break, they cover you with this really heavy apron. It's lead inside of there, and the purpose is to keep the X-rays from reaching parts of you that they don't want them to go. And then if you had neutron emission, that is only stopped by feet of concrete. So if something was giving off neutrons, even that lead apron wouldn't be able to stop it. We're going to look at all of these in greater detail. So in the coming slides, take some notes on the different types of radiation so that we can work with them some more. Okay, first we have alpha decay. So take a moment and copy down what's on this slide, and then I'll do some explaining. So if you have this down, you can see that what creates alpha decay is a nucleus falling apart, but very specifically, it breaks apart and gives off 2 protons and 2 neutrons. So we need an easy way to represent this 2 protons and 2 neutrons. So what we do is we represent it this way. We call it an alpha particle, and how we represent an alpha particle is right here. Let's change my highlighter color. Is right here. We have this way, or we have this little alpha symbol. The one that's the most useful to us is this one right here that I'm making in the largest yellow section because we're going to be able to use it in some problems like down below. You need to know what it's stopped by. So if you were taking a test, you would need to recognize this as an alpha particle. So if I gave you a test question, I gave you this equation, and I said, what type of radiation is this, or what type of nuclear decay, I would expect that you see this and you say, oh, it's alpha decay. Now, one of the things that we're going to do for these is we're going to have to do these equations. And the basic rule of the equation is this. Our two sides have to be equal to each other. So if you look at this one, we'll switch back to highlighter here. The top number on this side is 218. So the top number on this side has to add up to 218. We have 214 plus 4. Well, guess what? That adds up to 218. Well, you know what? Our bottom numbers have to be equal as well. So if I switch colors for the bottom numbers, this bottom one is 84. Well, if we switch over here to the other side, let's use something we might be able to see through. Over here, the bottom numbers still add up to 84. We have 82 plus 2 is 84. So if we are given some generic equation, like if I have 235 92u, and your practice problem says, write the equation of the alpha decay. What you're going to do is you're going to know, well, an alpha particle is 42 He. So what I'm going to do is I'm going to make sure that all the numbers on this side add up to the numbers over here. 4 plus something is 235, and a little bit of math will tell me that that is 231. 2 plus something, excuse me, adds up to 92. Well, that has to be 90. Now, how do I know what letter goes right here in this? We're going to use it like an imaginary space. I won't leave the box there because surely someone will draw a box around everything. So what's going to go there is going to be based off of this. Remember, we just said that the bottom number is the atomic number, and the atomic number tells us the identity of the element. So you can hear me getting out my reference table because I didn't have it out ahead of time. I'm not prepared. Element number 90 is TH, thorium. So I write TH right there because that is the symbol of the element that's going to go there. And again, let me get rid of this line because somebody will copy it thinking that it has to be written there, and it does not. Okay, so you should know the symbol for an alpha particle and be able to fill this in. So what if I do this with something different? So like what if we do the alpha decay right here of thorium? We do 231 90 TH. And this time you have a problem that already has the alpha particle written in, and then it's got a blank, because you have some practice problems that look like this. There's a blank there. Well, what do? You do the math and you just fill in the blank. 4 plus something is 231. The easiest way to do that is just subtract across. 231 minus 4 is 227, and then 90 minus 2 is 88, because 88 plus 2 is 90. Now, element number 88 is, I'm looking, that is radium. So I put in Ra for radium. Okay, so that's about the level of difficulty that these could be. It's that simple. Identify that it's alpha, write the whole right side of the equation, or just simply fill in the missing blank. Now let's look at beta. Take a moment again, copy down what's on the slide because you're going to need it, and then replay so that we can do some explanation of this. So you can see here that beta is also when a nucleus breaks down, but this time it breaks down into different things. It breaks down into a proton and an electron. The proton is going to stay in the nucleus, which is actually going to change the element. So if you think about it, if a proton stays behind, what it's doing is it's gaining a proton and it's losing an electron. The electron is going to be emitted. So we call these electrons that leave beta particles right here. How we're going to symbolize that this time is with 0, -1 for the electron, or with the Greek symbol, the Greek letter beta for, well, beta. The most useful one, in my opinion, is the isotopic symbol one, because as you can see down here, we're going to put it in the equations. You also need to know what beta can be stopped by. So, like last time, this still works out the same. The two sides have to be equal to each other. So, yet again, let me get happy with the highlighter here. This side is 210. Well, let's add up over here. 210 plus 0. That's the same. 210 plus 0 is 210. Okay, look at the bottom one. 83. So I need this other side to add up to 83. Well, now wait a minute. This says 84, but we're adding a -1 to it. 84 plus -1 is 83. So when it comes down to this, What do you need to be able to do? Well, you need to be able to look at this and go, well, that's beta. It's beta decay because I see this, and I recognize that as a beta particle. That's one thing that you need to be able to do. Like last time, we could do the beta decay of the same thing we did last time. We could do the beta decay of uranium-235. Well, how do we do that? This time we know that a beta particle, if I'm doing beta decay, I'm giving off a beta particle. So I write down the beta particle, and then you can still subtract across. Subtracting across works really well. 235 minus 0 is 235. 92 minus negative 1. That ends up being 92 plus 1, which is going to be 93. And if you stop and think about it, negative 1 plus 93, it's 92. 0 plus 235 is 235. So how do I figure out what goes right here where my cursor is? We look at the reference table. Element 93 is neptunium, Np, so we fill that in. And again, this could be just as easy as last time if someone gives me, oops, that should be a 0. I don't know why sometimes I make that pop up. After a whole semester of this, I still don't know. So if we're given the beta particle and a blank, then this is even easier because I don't have to think about what a beta particle is. I just simply need to be thinking that the numbers add up to the same thing on the other side. So 0 plus something is 231. Well, it's 231. Or we could subtract across. 231 minus 0 is 231. Negative 1 plus something is 90. Well, that'd be 91. Or we subtract across. 90 minus negative 1 would be 91. Well, who is 91? According to my reference table, it's Pa. It's protactinium. So we fill in the symbol Pa because that's element 91. So the same three things: identify the type, fill in the whole right side, or fill in the missing blank. We're almost done. We have a couple more things after this. First, we have gamma. You're going to like gamma even better because gamma only gives off energy. It's represented by this little Greek symbol. I think of it kind of like a Y with a loopy tail, so I just kind of do this, make it look like that. It's best I could do for it. It does not give off any matter. So this one gives off two types of radiation. Right here it gives off beta, and here I know it gives off the gamma radiation. So if it gives off gamma, you're not going to have to do any kind of math. The math is done because of the beta. It can be stopped by feet of concrete or lead. You know, a little bit of concrete would stop it. The neutron emission is like the ugliest kind. So you're not going to have to do anything with these other than just identify that it's gamma and what could stop it. We have a couple more possibilities for emissions that you do need to know, and I'll highlight the things that are what you need to know. Neutron emission. This is the symbol of a neutron right here. Now, neutrons have mass, so that's why they're given a mass number of 1, but they don't have charge, hence the number down here of 0. Now look, the math works exactly the same. 234 is equal to 1 plus 233. And 90 is equal to 0 plus 90. So you do the same kind of math, but you would recognize that, you know, this is a neutron. Now over here I did it and I put a 2 in front of it because I wanted to point out to you that when you do it this way, you multiply. So this is the same thing as saying 1 0 in and 1 0 in. There's 2 of them. So when I do the math, it's 2 times 1 is 2. There's a mass of 2 right here total. So 2 plus 232 is 234. And the 0, well, 2 zeros is still 0, so 0 plus 90 is still 90. So if you have a coefficient in front of it, you just multiply the mass. Now this one here is a positron. A positron is basically the positive version of an electron. It has a mass of 0, so it's got a 0 up top, and it's got a plus 1 because it's a positive charge. This is your symbol for a beta particle, except what's happening in this one is it's written on the left-hand side. So as far as the math goes, it's still the same math goal. Left side equals right side. 234 plus 0 equals 234, and 90 plus negative 1 equals 89. You'll actually see some of these problems in your worksheet where you'll have neutron capture as well. And so you'll have 1 0 in written like this, and then you have to figure out the other side. So this is a game of make the two sides equal. 234 plus 1 is 235, and 90 plus 0 is 90. So what is this going to be? Well, it's still going to be thorium. It just changed into a heavier isotope. The mass number changed. That's all that happened. So if you end up with multiple things written, you still just make sure that the two sides equal each other. Sometimes this blank is left. So you need to recognize that if there's a positive 1 on top and a 0 on the bottom, it's a neutron. And if we go back for just a second to look at this, I happen to think about, I didn't explain this part. Why is an alpha particle written as a helium atom? Well, because if you have an atom of helium, you have, this is the isotopic symbol for helium. What you have is you have 2 protons because it has an atomic number of 2, and since it has a mass number of 4, it has 2 neutrons. Well, look, that is the definition of an alpha particle, and that's why they use this to represent it. I didn't think about mentioning that back here. So now that we have these, I have 2 definitions for you, fission and fusion. You just simply need to know these, that fission is the splitting of nuclei, and I actually don't have this written down here. So fission is the splitting of nuclei, which means that they get broken apart. Nuclei is plural for nucleus. They get split apart, and it releases great amounts of energy. This is what we do in nuclear reactors, is nuclear fission. Fusion is the joining of nuclei. And where this happens commonly is on the sun. It's in stars. Our closest star is the sun, of course. It releases great amounts of energy, so much so that we haven't really been successful at doing this large scale and be able to keep temperatures down enough to contain it. If we ever could, then this would certainly be more useful as far as making energy than fission. So this is kind of trying to do already done with the fission part of it. Okay, now something else to know about this before we get to practice time is we said a long, long time ago that the law of conservation of mass has to be obeyed. And with nuclear reactions, that is not the case. Like, matter is actually destroyed and converted into energy. So this is one place that it's an exception. It didn't become an issue until Einstein created the first atomic bomb, and then he led us to the nuclear age, where the law of conservation of mass kind of gets broken for a while. Okay, so know those definitions. Now it's practice time. You have a practice sheet that is basically you identifying whether something is alpha, beta, gamma, or what type of decay, and filling in those nuclear equations. I don't think it will take you very long whatsoever to do. If you need help from me, let me know during office hours or send me a message.